Alright, so we're looking at net change, and we're going to look at some properties too. So net change is looking at the, like what's happened in terms of displacement. So if you go from your desk to the fridge and then back to your desk to do more schoolwork, then your net change is 0 because you got back to where you started. The distance that you went away is equal to the distance that you came back, so the net change is 0. That's different from like the total distance traveled, which would be the distance from your desk to the fridge and then the distance from the fridge back to your desk. That's how far you've walked. But the displacement is 0 because you're back where you started at. So we're going to talk about some theorems and some properties, and let's get started. So, the net change theorem. I think our book might be the only one that I've seen so far that calls this something, but it is helpful. So it's basically another look at the fundamental theorem of calculus, where you have the new value of a changing quantity is equal to the initial value plus the integral of the rate of change, where we're looking at cap f prime of x. When we take our definite integral of that, then we're left with our function f evaluated at b minus our function evaluated at a, which is just our fundamental theorem of calculus, and then all this is just rearranging that a little bit. Take this f of a, subtract it over. That's it. Which is why I think this book is maybe the only one that actually gives it a different name. You don't have to call it the net change theorem. I don't think that's like a regular thing, but it's cool if you want to. It's totally fine. So, find the net displacement and total distance traveled in meters, given the velocity function is f of t equals 1/2 e to the t minus 2 over the interval from 0 to 2. So, the net displacement, that's just our integral, our definite integral. So, net displacement is just our definite integral from 0 to 2 of 1/2 e to the t minus 2, and we're integrating with respect to t. So that's what, 1/2 e to the t minus 2t from 0 to 2, and that's 1/2 e squared minus 4 minus parentheses 1/2 e to the 0 minus 0, and that's 0, that's a 1. So we're left with e squared over 2 minus a half. Oh, minus a fourth also. Minus 4 minus a half. So 4 is negative 4 is negative 8 halves. So this is negative 9 halves. Okay, so that's the net displacement. What about the total distance traveled? So we're looking at a velocity function that looks like that, which is with a rough sketch, something like that. So we have a negative distance and then a positive distance. So our thing that's moving, the object that's traveling, let's call it smiley face thing. Smiley face is going backwards from time 0 to time like a, and then thing smiley face is going back to the right from time a to time 2. So we need to figure out when our function, our velocity function, changes sign, so that we know that that's where our function changes direction. So let's figure that out. Let's see. So f of t equals 0 when 0 equals 1/2 e to the t minus 2, so that's 2 equals 1/2 e to the t, 4 equals e to the t, so t equals natural log of 4. So our a, in this case, this breakpoint between going from negative direction to positive direction, is at natural log of 4. So we need to break this up into two different integrals, from 0 to natural log of 4 of, and this is the negative of 1/2 e to the t minus 2 with parentheses around there, dt. That's one way of doing it. We could also go backwards from natural log of 4 in our lower bound of integration to 0 in our upper bound of integration, because that would also give this negative area as a positive value, if you're going backwards. And that was like from 2 lessons ago. And then we need this plus our definite integral from natural log of 4 to 2, which is where we're ending up, of our original function of 1/2 e to the t minus 2 dt. Okay, so what do we get? This equals, might need a little bit more space. Okay, so we have negative 1/2 e to the t, that's going to be negative 1/2 e to the t, plus, because the negative goes and distributes out there, so we have 2t from 0 to natural log of 4, plus, and then our antiderivative that we found before of 1/2 e to the t minus 2t from natural log of 4 to 2. I'm going to be slightly lazy and not put parentheses around my natural log, and that's okay. And let's just draw some space over here. So we have this equals negative 1/2 e to the natural log of 4 plus 2 times the natural log of 4 minus, parentheses, negative 1/2 e to the 0 plus 2 times 0 plus 1/2 e to the 2 minus 2 times 2 minus, parentheses, 1/2 e to the natural log of 4 minus 2 times the natural log of 4. Okay, so let's simplify. What do we get? We get negative 1/2 e to the natural log of 4 gives us just 4, plus natural log of 4 squared is 16, plus 1/2, and that's a 0. E to the 0 is 1, right? And then we have plus e squared over 2 minus 4 minus, parentheses, 1/2 times 4 minus natural log of 16 again. Okay. So now what do we have? Negative 2 plus natural log of 16, and then we're going to have another one of those. And we're actually going to have another one of those, so that's a 2 times that and a 2 times that. So that takes care of these. And then we have plus 1/2 plus e squared over 2 minus 4. Boy, okay, so negative 8 plus 1/2 plus e squared over 2 plus natural log, that's getting to be too big, 2 natural log of 16, okay. Negative 8 is negative 16 plus 1 is negative 15 halves plus e squared plus natural log of 16 squared. Yeah, number. Alright. Is it okay to leave a number like that? Heck yeah. It's more exact than trying to simplify it, but if you really want to, you can. Alright. So, some properties. So, even and odd functions are really, really nice. Why are they nice? Because they're symmetric in ways that we like. So, if you know that you have an even function, right, that's the way that we can say even functions, then you know that you have symmetry with respect to the x-axis, or sorry, the y-axis. This is the y-axis, and this is the x-axis. So, you know that for a negative value and a positive of that same value, you're gonna get out the same y, the same output. Which means that your area under your curve is going to be the same on the left side of 0 and on the right side of 0. And so, if you are evaluating a definite integral from negative a to a, so you're looking at the opposites of numbers as your inputs, of some even function, then you're going to get out 2 times or double what your definite integral is from 0 to a, from 0 to a of your function. So it's just taking this right side and doubling it, and that's the whole area. For odd functions, so that means that we have symmetry with respect to the rotational symmetry with respect to the origin, then, and this is really poorly drawn, I'm sorry, but the area here that we get is going to be exactly the opposite of what the area there is that we get for some a, negative a over there. So, since those all cancel out, we know that for an odd function, the definite integral from negative a to a of our odd function is 0. So, integrate that. Use the properties. So what do we get? This is an even function, is it not? So since it's an even function, we know that our definite integral from negative 2 to 2 of x to the 4th with respect to x is equal to 2 times our definite integral from 0 to 2 of x to the 4th with respect to x. And that's 2 times x to the 5, x to the 5, oh my goodness, 2 times x to the 5th power over 5 from 0 to 2. And do you see why 0 is so much nicer than having to plug in negative 2 and evaluate? I do. I really do. Okay, so we have 2 to the 5th power, which, because everyone has played 20, 30, 48, because, stuff, then we know that 2 times 2 times 2 times 2 is, I actually don't remember, what is this? This is 8, this is 16, 32, oh my gosh, okay, so we have 32 over 5, minus 0, oh wonderful, okay, so then we have 2 times 32 over 5, 2 times 32 is 64 over 5, and boom, there you go. So the properties are really nice when you have even and odd functions. Evaluating when their bounds are the same is really, really nice, because we can use the symmetry to our advantage. And when we're looking at net displacement and total distance traveled, those are different. The total distance traveled, we need to take into account the positive and the negative parts, because distance traveled means like how far it's going, not how far it's moved total. Like looking at the step tracker versus looking at the snapshot of like where you are. So net displacement is just looking at the starting and ending position and how those are different, and that is simply evaluating your definite integral. Total distance traveled, it needs to take into account when your velocity is positive versus negative, and taking pretty much the absolute value of that, which is what we were doing over here with breaking our definite integral up into 2 different parts and putting a negative in front of this part, because over here our function for our velocity is going to be negative, so we want to take the negative of the negative section so we get a positive area. And this has a name in our book, but isn't really named in other things, so feel free to not call it the net change theorem. Totally fine. Alright, this is a short one. It's pretty good. I feel like I should tell you a joke or something. Oh, this is one that my mom came up with. What do trees and dogs have in common? Limbs.